Okay, guys, so we'll start shortly in sometimes. Waiting for the audience. At 9:15, we'll start here. So, guys, let us start with the event. So, first of all, welcome you all for the event that fundamentals on deep learning. Okay. So, let us look previously what we have. Let us revise the previous things first at what we have learned about neural networks and deep learning. Okay. So here we have a PPT where I showed you in previous slides how neural network actually works. So as we saw that there is like these are artificial neurons, okay, that replicates human brain's neurons, and when some information is given to it, it computes it, it adjusts the weights. These are the weights, and then we get the output, right? So similarly, as I said you that in machine learning we train models, all right, and when we use neural network, when we have a data in CSV file, so at that time we use the machine learning. But when we have something data as images or some uh, languages or some different very varied values, at that time we go with artificial neural network. So artificial neural network is very a better choice to handle a varied type of data, and it maps and it works with your data set also, fits with. And then we have some activation functions like sigmoid and ReLU activation functions. So as I just for a repetition, I said that activation functions basically fires the neurons depending upon their nature. So sigmoid functions are used for decisions. ReLU functions are used to only capture the positive values, whereas the negative values are converted to zero. All right, so these are type of different uh, you know activation functions that fires the neuron. So it is like a structure where one neuron fires another neuron fires another neuron, and then it keeps on mapping unless we get an output. So I hope you guys are clear with artificial neural network. So today, what our major topic is that we will be learning about RNN and CNN. All right. So what are this RNN and CNN? So if you see this cat image, like here yesterday I have repeated this. So like when you give an input in the form of images or videos, then for that purpose we use CNN, convolutional neural network. The reason behind that is like neural networks work with only numerical values, but when you give it an image, so then you have to convert it into a vector, that is numerical vector. So how we convert it and how do we process send that numerical vector into the neural networks and how we predict the value. So today we'll learn about that in convolutional network. And in RNN, recurrent neural network, we will learn about how natural language processing works, how we deal with different types of series data, which requires RNN, recurrent neural network. And as you know, like one of the biggest example of recurrent neural network would be ChatGPT. So if you guys are interested in these things, then this video is for you. And so keep watching the video. Now I will call upon Shivam, which will start with the convolutional neural networks, and then we will go on with the recurrent neural network, and then we will end our session, because these two architectures are very important in the neural networks, whereas ANN is just a dense network. And yesterday we discussed this. So today our fundamental goal is to discuss about convolution neural network and RNN. So just a second, I'll stop sharing the screen. Shivam, you can share your screen.
All right, Fazan, thanks for the short revision. So now I'll share my screen. I hope the screen is visible.
Yes, it is.
So the topic that we're going to now study is convolutional neural networks. So let's see that what is actually CNN. So a convolutional neural network is a type of deep neural network designed to process data that has a grid-like structure. This structure is usually found in images and videos. CNNs are used in a wide range of applications, including image and video recognition, then object detection, image classification, and also in image segmentation. The key features of CNNs is their ability to automatically learn and extract features from the input data without requiring manual feature engineering. So this is accomplished through the use of convolutional layers, which apply a set of learnable filters to the input data, each of which extracts a specific feature from the input. We'll see that into the near future in the coming slides. CNNs are particularly well suited for image and video recognition tasks where they can learn to recognize complex patterns and objects in images and videos. This is achieved by stacking multiple convolution layers together, with each layer learning increasingly complex features from the input data. In addition to their ability to automatically learn features from the input data, CNNs are also able to handle variations in the input data, such as changes in lighting conditions or image distortions, or maybe there is some blur in the data. So this kind of noise doesn't affect CNN. CNN is still properly able to recognize the features in the image. This is achieved through the use of pooling layers, which downsample the feature maps produced by the convolution layers, reducing the sensitivity of the network to small variations in the input data. So overall, or in conclusion, we can say that CNNs are powerful and versatile tool for processing grid-like data and have been used to achieve state-of-the-art results in a wide range of applications. So now let's take an example. So in this example, we see that there is an image of koala. So as a human, we can definitely see the features such as the koala's eyes, which are black in color, his nose that is flat and pretty large, we can see, and the ears, we can see that the very ear is very fluffy. We can, like, our brain recognizes these features naturally, but how does the computer understand? So we can see that the computer is going to extract features like such as koala's eyes. This is all done by CNN's convolutional operation. We looked at into the later slides. For now, let's just understand that the convolution layer is going to extract the features like koala's eyes, whether the eyes are present or not, whether the koala's nose is present or not, and let's say whether koala's ears is present or not. Now, let's say that if these three features have been found, then our model is pretty sure that koala's head is going to be present into the image or into the test image that we are checking. Same on the other hand, also you can see that if our model is able to recognize or detect the koala's hands, and if it is also able to detect the koala's legs, then the model is pretty sure that the koala's body is present in some part of the image. And once our model is sure that koala's head is present and koala's body is present, then our model is going to predict that there is a presence of koala in an image. So that's how it works for a computer to detect any object. So that is how CNN is applied in object detection. Now let's go a bit deeper into the combination operation. This is the mathematical side of it. Like, I've taken an easy example. On the left side, I've taken this image. Now of course, this doesn't look like an image because this is an array of numbers. Image is an binary image, so it has only got two values, that is -1 and 1, that is black and white. This is a binary image, but in real life, of course, we have got colorful images. So there are going to be RGB values for each of them. So there will be three channels for them. But for the simplicity's sake, I have taken this image. So what we are going to do is that we are going to apply this filter. This green box is the filter. This green matrix is actually used to detect the presence of a circle or a loop, we can say, because the boundary is 1 and the center is -1. So we are interested in detecting a circle in an image, or we can say a loop kind of thing in an image. So we are going to apply this filter throughout the image by sliding it towards the each rows and column. And by in the first case, we see that the 3 by 3 grid is fitting on here. So what we are going to do is we are going to do a dot product on this thing. So by multiplying the filter with the first set of input. So we are going to multiply this -1 with the first one, this one with this one. So it is just a multiplication of respective, we can say the respective positions in the this grid. So once we multiply them and add them, we get some value, and then we are going to take the like divided by the 9. That's the basically we are taking the average of it, and whatever the averages come, we take that and insert it into this matrix. Now, what is this matrix? Now, this matrix is the feature map. So this feature map is going to help us to detect the presence of an object. And the object we're interested in this example is a circle. So let's see the next slide. So after we slide the this thing filter to every part of the image, we are generating our feature map. So we can see that this requires a lot of computation. See, I've taken an easy example of binary image, but in real life we have got RGB color images. So of course the computation is going to be increased, and the values are not going to be 1 and -1, but rather the values are going to from 0 to 55. We know that RGB values for red, blue, and green, it ranges from 0 to 255, that is 255. So, and also this filter map, this filter is of 3x3. That is, it has 3 rows and 3 columns, but it is up to us that whether we want to take 2x2 or 4x4, it's up to us. So yeah, when we generate the feature map, these are the values that we are getting. So as you can see, this feature map is generating the continuous values. So the after we apply the convolution operation to the input array, after that we are going to, okay, first of all, let's see the benefits of convolution. So first benefit is connection sparsity reduces overfitting. And what this means is that it is not going to connect each and every node in the neural network to every other node. So it is basically reducing the overfitting by not connecting every node to the other. So that is the benefit of convolution operation. And convolution plus pooling gives location invariant feature detection. Now, what does this mean? It means that, okay, let's say here our image koala is in center. Koala is in center. So what if the koala was flipped? Let's say this image was flipped by x-axis or y-axis. Whether our model will be able to detect it or not. Let's say the koala was not in the center, but on the right side of the image, or let's say in the left bottom of the image. So will the model be able to detect it or not? So by applying these convolution operations, we make sure that our model is going to recognize the object wherever it is present in an image and not just localized. It is not learning from localized pixels, but rather it is trying to learn the patterns that are learned from the feature map. So this is done by applying convolution plus pooling. So pooling we are going to study further ahead. So for now, just understand that there is a topic of pooling which is going to help us to make the model understand invariant features. And finally, I've got parameter sharing. So once we learn the features, the parameters are updated, and these parameters are then passed on to other nodes also in order to detect that object in different ways, as I said earlier. So now, once we have got our feature map, that is the continuous values, we are going to apply an activation function to it. Now, which activation function we are using here? That is the ReLU. And as Fazan has taught us on the first lecture itself, the ReLU activation function. Again, I would go through it again because this is a very important activation function. So let's first understand the graph of the ReLU. So what ReLU is going to do is it is going to take continuous values as input, and whatever the negative values it is going to see, it is going to convert it to zero, and whatever positive values are there, they are going to remain the same. So as in the graph also we can see that whatever negative values are there, they are getting converted to zero. On the other hand, the positive values are plotted through an identity function. That identity function means x equals to y or y equals to x, we can say. So the values are going to remain same. And in our example, this was our feature map that we generated from the previous step, that was combination operation. So after applying the ReLU function, we see that all of the negative values are getting converted to zero. But on the other hand, we see that the positive values are the same as they were before. So that is what ReLU function is doing. And why we are doing this in the first place? Because this is going to introduce non-linearity in our model. So let's see the benefits of ReLU. As I said, it introduces non-linearity in our model. So, and it also speeds up training and faster to complete. Now, what does this mean? Let me take back to this slide. Once we see that zero has been previewed, so it makes sure that our computation is going to be fast. It is only going to focus on the features that are actually positive and are contributing to our object detection or maybe image classification, and not on the features that are not contributing anything for our. So we are just going to remove them. That is, we are converting them to zero in order to increase the computation speed. So that is the role of activation function in CNN. Now let's see another main part of the CNN, that is pooling. Now what is pooling actually? Now let's say that we have an image of size, let's say resolution 1920 x 1080. Now that is a very large image, and of course it is going to have RGB, so we need to multiply it by 3, as there are 3 channels. That is one channel for red, one channel for green, and one channel for blue. So once we go start computing the combination operations and perform the redo operation, still the dimension is not decreasing, we can see. But by doing pooling, we actually reduce the dimension of the this thing image. So that actually saves us a lot of computation, and only the main features are passed down to the succeeding layers. So pooling is the method in which we are reducing the dimensions and reducing the computations and extracting the main features, and what we can say that we are passing it to the next layers. So how pooling is achieved? We have got two methods, that is max pooling and average pooling. So in max pooling, I have taken an example where I've got a 4x4 this thing feature map, and after applying 2x2 pool size, what I'm doing is this first four cells in green colors, I'm going to take the max value out of this. So 100 is the max value. That is pretty evident from the image itself. 100 is the max value. And from this right top four cells, you can see that 184 is the large value. And from the left bottom, since all the numbers are same, we are going to just take the 12 and put it in the feature map after applied the pooling operation on it. And lastly, we have got 45. So we can see that we reduce the dimension from 4x4 to 2x2. So this is also actually decreasing the computation for our model. And on the other hand, as you have guessed the average pooling, you might have guessed it already, that we are just going to average these all four values. That is, we are going to add them up and then divide it by 4. Then we get the value of 36. And similarly for the other cells also. And we apply this 2x to reduce the dimension. And it is not always fixed that we take 2x2 pool size. We can also take 3x3 or maybe 4x4, whatever our choice is. If the image size is very large, then we can improve the, not improve, but increase the pool size. And
Just a minute, guys. Shivam is disconnected. He's trying to reconnect.
Hello, am I audible? Okay, okay, let me share my screen.
Yes, you are.
I think some technical issue was there. I was disconnected. Okay, let's continue from where I left. Yeah, I think I was here pulling. So yeah, there are two types of pulling: max pulling and average pulling. So as I said, that max pulling, what we're going to do is we are going to take the first four cells and we're going to just pick the max value out of it. That is 100. And in this top four cells that on the right side, we are going to take the max value out of these four cells. So that is 184. And similarly for the bottom cells, and respectively, I have put it the value. So that is how the max pooling works. So we can see that we have reduced the dimension from four rows and four columns to two rows and two columns. So this is also going to save us some computation time and processing time. And in the average pooling, we see that we are taking the average of these four cells and then inserting into the feature map the answer of the average. And respectively for the other cells also, these four cells average comes out to be 80, and respectively for the blue color it is 15, and this one is of course it is 12. So by applying this pooling operation, we make sure that our dimension is getting reduced to our desirable size. Now you might be thinking that why we have taken as 2x2 pool size. So there is no compulsion to take 2x2 pool size. We can also take 3x3 or maybe 4x4 according to our need. If our image size is very large, that is the resolution of the image is very large. Let's say 1920 x 1080. Then again there are three channels for it. That is for red color, green color, and blue color. So for that we can actually take the pooling size of 4x4 so that the dimension is getting decreased to a shorter dimension. So benefits of pooling, as I said, it reduces the dimensions and computation. So we are not going to look into ahead of it. Then it reduces overfitting as there are less parameters. Now, actually, when we are removing the features from the array, we are making sure that the parameters are also getting reduced. So this makes sure that our model is not going to overfit to the training data, and rather than that, it is going to learn the general features. So that is what our need is. The model should work on out of sample data, not greatly on the on sample data. And model is tolerant towards variations and distortions. Now, this was the benefit of convolutional layer itself, that our model is going to be tolerant towards variations and distortions. This means that let's say the object is not in the center of the image, or rather the object is on the left side of the image, or maybe the wherever it is, like right bottom. So the model should not be like not detecting the object. It should detect it, right? That is what we are making this model for. It should detect the object wherever it appears on the screen. So that is why we are doing this pooling in order to make the model learn the general features of these objects. Finally, I have summed up the architecture of CNN in this image. So what we have is a collage image, the training data. So we are going to pass this image as an array as a 2D array to the convolution layer, that is followed by ReLU activation function. After that, we are going to apply the pooling operation. And after we get the pooling, we are again going to apply the convolution layer, then again the activation function. And then again, we apply the max pooling or average pooling, whichever we have selected. And after that, we see that we are flattening this 2D array to a 1D array. And then there's a dense neural network ahead of it. So the everything behind this yellow dotted line is feature extraction. So this thing, convolution, then radio activation function, then pooling operation. This all are these things. They are going to help us to extract features from our training data. But on the other hand, this right side is a dense neural network. That is the flattened dense neural network. So this thing is going to help us classify the object, that whether the cola is present in the image or not. Or let's say there is no cola, but rather a dog is there. So if there is a dog, then it should classify it as dog. So this dense neural network is going to help us understand that. So yeah, that is just all about CNN architecture. Now I would like Fazan to continue with your next topic.
Okay, Shivam, thank you so much for a great presentation and sharing knowledge about convolution neural network with us. Now we could have a look how a CNN code would look like if we build a project, right? So just wait a minute and I'll share my screen. I hope my screen is visible. All right. So let us look how an actual code would look like if you want to classify between, looking at classify between something like binary classification based on CNN, right? So we can see here I have the code here with me. So before actually going to the code, I want you to understand what is my data set. All right. So a data set and what is the context of building this project. So my context project is about classification of aquatic animals and the garbage in the ocean. All right. So well, when we work with convolutional neural networks, we actually are not working with CSV data files or something like that. So how do we conclude with our data set? So for our data set, we have to first let me show you my data set actually. Just give me 2 minutes. So this is my data set. If you actually see, this is like in a data folder. I have two class, like two images. See, I have to classify between animal, aquatic animal, and hazardous material, right? So I have to train my system with it. So you can see I have a lot of aquatic animal images here to train with. Have different aspects of animals. The screen visible. All right, I guess my screen is not visible. Just wait. I hope it's visible now. Okay.
Yes, yes, it's visible.
Okay. So, so I was saying, like when we work with CNN projects, we to first train our model. So what our context was that we are classifying between marine life pollution and garbage. Marine life pollution, aquatic animals. So this is my training set images where I have taken a lot of animal species, aquatic species, and this is also my training data set where hazardous materials are present. That is cardboard, garbage, and all. All right. So this is my two training data sets. Why these are my testing images I have here with me. Okay, so when we work with our model in the CNN, so first of all we import in TensorFlow. So yesterday I gave a lecture on what is TensorFlow and how it's used basically for numerical computations in the background, and Kera on top of that, the front end of Keras is built. Then we are using import OS, so this is used to navigate through file structures. So it is important part in your CNN as you have saved your images, and images are not a numerical value, so they have to store in a file, and then we access it through the OS. Then we see what are the uses of OS. So os.parjoin will return you the folder and the file name. Right. So whatever inside the folder name, we have different files that will be showed to you. And then we have os.list directory folder. So this will list down all the files in a particular directory. I guess my screen is not visible. So some technical issues. Can anyone cross check my screen is visible? Okay, so I guess it's visible on your YouTube. Uh, we had some technical glitch with the portal. So I was saying that first of all, what we do is import this CV2 library, computer vision library, that is used to read images as an input in because We are not working, as I said before, we are not working with numerical values since we have needed the CV2 library. Then we are working with image HDR. So image HDR basically library to check for the files extension, particularly images. So like what type of image, for example, JPG, JPEG, and PNG, these type of images. I'm using matplotlib, import pyplot as PLT. This is sub library of matplotlib to visualize images. All right. So firstly, we are creating, storing the data folder into our data directory. All right, and then we are passing the data directory to our list directory. So what I said before, like when we pass the list directory into the folder name, then we get list down all the files in the directory. So we can see we have these two images list down: aquatic animal and hazardous animal. So what our first task is to remove dodgy images. So to check now let us see how we remove dodgy images. Okay, to check every image in the folder first of all. So if you want to check every image in the folder, as I said, os.list directory will take you into that folder. All right, and then it will list down all the files. And apart from that, it will have a path.join. So we are also using path.join, which will help us get into the folder. This. So now we have entered into the folder. Okay. So into that folder, what we are actually printing is we wanted the list directory. List directory is on the outer side of the os.path join. That's why what we are saying that when we are going into path join, okay, we want to list all the directories of data directory, especially the hazard materials. So we are specifying that we want to go in and print all the images that are present. Okay. So what we do, then we have accessed the hazardous materials images. All right. Now, like we have explicitly created a standard list of extensions of images as JPEG, JPG, BMP, PNG. These are the standard images that we work with. So this is explicitly created a Python list so that we can loop through the whole these file folder, and then by using identity functions we could say that if this is present in this list, and if it is present, then you just have to keep it. Otherwise, you have to discard it. All right. So this is how we do it. So iterating through images and removing faulty images which does not match with standard extension list we made. So this is how we actually iterate. So this is my iteration. I'm iterating into the data directory, that is my aquatic animal and hazardous folder. All right. So for image OS in this directory, os.path join data directory and image class. So this will print through each image. This will iterate through each image in the above two folders. All right. So as I said you before, like then what we are doing, we are targeting individual pick from the above two iterations, and then saying it's a and send then swing in a variable. So image path is stores a particular individual images. When we look through these images, okay, we look through this, we are storing a particular individual image in this. All right, and then after that we have a try and catch exception block. All right, so in try, what we are saying that when image is equal to imread. All right, so imread allows you to open the image using OpenCV. We cannot open directly into our program directly, so we need something to open with. So we use the computer vision method, that is imread. All right, we read it into the image folder. Apart from that, this reads what image extension is. As I said, you IMHDR is used to get the image extension. So that particular, that is, see, I said this contains individual pic. So that individual pic is first of all read it in IM and it's opened, and then for that IMGHDR dot what is that particular extension of that image, and then it's stored in the tip. So we have two variables now, image and tip. So if that image extension is not in, this is my identity operator. Right? So if this is not in image extensions, this is not image extensions, that is explicitly list that I have created over here. If that doesn't match, then we have a formatted string. That image does not exist in the list, and then we format it with the image path, that particular image address, or you can say the name of that particular image, and then we could remove it os dot remove using the os dot join, or the operating you say os library. Right. And then we have an exceptions like to handle, suppose if the format if there isn't some issue with the image, so you don't have to crash your iteration. So we just have a exception that if the image is if it has some issues, or if the web app files or are directly it is not into that explicitly given list, so then we could just say print the message that there is some issues with the file or image. Okay, so we could directly understand that there is some issue with the image. So now it's time to load the data. All right. So now we load the data into our, as we previously have said. So when we actually read the data, so we read it in different way. We use the keras, and then we have inside that details, and then inside that we have image data set from directory. This method, like this library, helps us to read the data from our directory, and then it will auto. So what is the functionality? So it automatically to data set. So there's some particular format that you have, and you need labels and you need classes also. So it automatically convert images into data set and also identify two classes. How we can see that it has found 2015 files belonging to two classes, that is hazardous, the two classes talking about is hazardous materials and the aquatic animal. All right. Then what we are doing actually, so we are actually passing the image through the numpy iterator, and it converts the raw data into a numpy array. So we are actually converting our images into a numpy array, and then we are allowing to access the data from the pipeline, and then we are creating a batch iterators. Okay, so we are creating batch. So batch is something that is used when when you want to load your files. Like for example, at one iteration I want to pass this much amount of files or this much amount of images. So that is the batch iterator. And so these are our image, as I said. See, this is the values. This is the values that we are working with. So we have numerically converted things now. Yeah. So and it also has labeled it. So this is the label array and this is the image array. Okay. So now what we will do is, like, first of all we will plot our images, like as it has said that I have identified two classes. So it has already automatically identified two classes, right? So to print that automatically two classes, we would see that it has given trash one, whereas it has given aquatic animal as zero. How did it identify that you have to give one and zero? This is because I have separated the folders in the data file only. That's why this has happened. All right. Then we go with the pre-processing of the data and then scaling images between 0 and 1 instead of 0 to 250. If I see working with a black and white or binary image is better than working with RGB, this is the only reason with this is because you don't have a lot of computations, because in RGB you have 256 value for red, 256 values for green, 256 values for uh, blue. All right. So if you convert it into binary, then it's 8-bit digits. So it's really able to do the computations. Instead, we could go with a binary image such as black and white, so we could give a 0 1 0 1 type of images. Then we have done that thing in here. If you see that we have divided it by that number, and yes, so if you do this, this is lambda function I said yesterday. This is anonymous function. All right, and this is the expression that we are dividing our x with the 255, 255. So this intensity will be decreased to black and white. All right, and y is my labels. I'm just passing the labels. So x is the images. So I don't want to decrease my, because there is no need to decrease the labels, as labels are just some text. But I want to decrease my image to binary. So that's why I'm dividing it by 255. All right. So now I am plotting it, and I could see that similarly my trash cans and my aquatic animals are given zero, and trash things are given one. So now splitting the data set. So in conclusion, neural network, it is important to split your data sets. In machine learning, you used to split in train and test, right? So, but here you can also split your into three parts, that is train size, and then that is 70%. Then you have validation size, that is 20%, and then you have test size, that is 10%. So if I print that size, you can see 63, 18, 9, and total. If I see, then there's a 90 images. So matches the total number of batches means it's correct. So see, at above I said you that we have created a batch. So if this number matches your batch value, then this means that okay, we have not left any of the image. Okay, we have taken consideration in proper 90 images in our batch. Okay, so allocating the train and test valuation. So this is how we give values to the train value and validation and testing data set. Testing. Okay, so we say that we use the skip functions or take functions. So for train we have take train size, then data dot skip. We have skipped the train size because we want validation dot take validation. Then we have this method that data dot skip train size plus validation size dot take test size. So this is how we pass the train, validation, and test values into the variables. Then we are building the CNN models. So as I said, Keraza used to build the models, and and we have built it. As I said, that Keraza used to build the front end, and behind the back end we have computations TensorFlow, right? So we are importing the equation model, and then as Shivam said that we are importing convolutional layers, max pooling, 2D, dense, and flattening. These were discussed in the theory class, so I won't go much look into this. So we have created an object for this sequential class, and then we are creating our uh, layers sequentially. So this you can see that we are adding a layers dot add method, and then we are saying that we need convolutional layer with 64 filters and by 3 by 3 filters, whereas our activation is equal to relu and input shape is 256 comma 3. This is the input size of the images. All right, and with a similar way, we are creating many layers, sequential layers here, and then we are performing with the relu functions. We are passing here. So we are differing into the filtration. That is, here we have 64. Here we are doing 32. Here we have filters that are 32. We have 32, and we have 120. So it totally depends upon you. You have to play with these values and understand which of the values fits best for your prediction. And this is just try and error. And whatever value suits for you, when whatever value, because these are the filters that fetch your feature. So it's totally depend upon a dry and run thing. So then I'm passing this flattening layer, and then here I'm creating a dense layer as neural network to 56 neurons with activation function as a relu, and then I have one sigma activation function where I have this one neuron that will say me that is 0 or 1, either 0 or 1. And then just yesterday, as I said you, this is the that the compilers and the loss validations that we use, binary cross entropy and all, to minimize the training errors and make the model better. But this is the summary of my models. These are my hidden layers, total hidden layers. All right, and this is how we are training. So we are training it for the epochs of 20, and validation and callbacks. See, these are the values that we want. So in validation data equal to val, right? This validation will be, so we are passing the val values in the validation data, and we have callbacks, that is tensor word callback. Okay, so this gives us the callbacks, like how precisely our machine is actually identifying and training upon the images. So this is how we train. Yes, I have showed you this in the first class of the neural networks. So this is how it trains. Okay, so as we can see, the loss is decreasing continuously. It was in 0.2501 for 20 blocks I have done, and it has drastically decreased to show me. Yeah, so it has 0.0, and accuracy has increased with the time. This is a training accuracy. This is the validation accuracy. All right. So, and this is the validation. This is the score. All right, 0.97. This is my validation loss. This was validation loss, and this is my validation accuracy. Sorry. Just like that, we can print the plot performance by plotting the validation loss and the loss. So we could see that loss is decreasing, and eventually validation is also somewhere it is more, and then it is decreasing. So it's a good sign that at the end things are the loss are getting decreased. All right, and you can see the accuracy is going increase. So that is a good sign. So when we evaluate the model, we then predict the values. All right, then we predict the values, and here are the predictions ready with the answers. So as I'm using the sigmoid function, as I said you before, so it gives me value between 0 to 1, right? So values could be like 0 point something something. So our threshold is 0.5. Below that we have aquatic animals, and above that we have a garbage detected. So this is my fish passing, and when I'm passing it, I'm passing it to Amity library that I've used computer vision. And then if we see our model has predicted. See, these things I've covered yesterday. I mean, in the neural network in the first class only, and the number that it has projected is 0.11 after getting into the sigmoid function. So it's 0.1, which is lesser than 0.5. So you have to print, such as if it is greater than 0.5, then it's a hazardous material, whereas if it is not, then it's an aquatic animal. So this is how you build a project in your uh, you know convolutional neural network. So this is a little uh, higher process to work with. But if you work and understand every single part of the function, what it is doing, then it is easy for you. All right. So this is how we work with CNN. So now let us get with the RNN part. All right. So I'm just closing this code. All right. So we'll be starting with the RNN part. That is the recurrent neural network. Okay. So let me grab a pen for myself. So basically, let us go with the definition of what is RNN. All right. So a recurrent neural network is a type of neural network that is designed to process sequential data by maintaining a memory of previous inputs. This allows RNNs to capture temporary dependencies and make prediction based on the context. So we have discussed two architectures now, ANN for independently, ANN, and we have discussed CNN. You see, we in this both we have in ANN we work totally with the numerical values. In CNN we work with the image values. Whereas in the neural network, in the recurrent neural network, we work with the time series models. Okay, time series data sets. So what could be a time series data set? Time series data set could be your it's the text that is, hi, my name is John. Time series could be your company stocks graph that is changing on an instance such as 2001 to 2003. It could be a speech that is converted into a this thing waves. So a DNA sequence, so anything could be a recurrent data set for the recurrent neural network that have a series, that have a sequential, that is sequential. Right? So this is an important word for sequential. So in ANN we work with numerical values, CNN we work with images, and in RNN we are working with sequential data. All right. Just give me 1 minute. I'll grab my mouse. All right. So what I was saying is that let us first understand what are the difference between non-sequential data and sequential data. All right. So non-sequential data are also known as unordered data. It refers to a type of data where the order of the data points doesn't matter. For an example, if I'll say that I'm giving you data of a person and giving you the IQ, his IQ I'm giving you, then I'm giving you his marks, and then I'm giving you his gender, and I'm asking you whether if this person according to this will be placed or not. I mean, placement will be done or not. Okay, so this is a question. So let me ask you, like, this is, say this is an independent value. Okay, so put into a neural network. All right, when you put it into a neural network, you can put the in we have different layers, and then we have an output. So when you put into a neural network, see here I have put it the IQ. Here I have putting the marks. Here I am putting the gender. Do you think, like, if I interchange this values, will it affect the placement? The answer is no. Why? Because they are independent value. They are not a sequential value, and they doesn't have any sequence. They're not related to each other, and they are independent values. But we can relate them with as features, and then we can predict this placement using all this network. Now, understand what is sequential data. So, sequential data refers to a type of data that is ordered in time or space, where the the data point matters, right? So now what does this mean? Now this means that now the sequence matters, right? So as I said, like if I write that hey, my name is John. If I write this, my name is John. So do you think I could transfer this as name my hey, John is no, right? We need a sequence. We need to follow a pattern that is hi, my name is John. If we pass it randomly, then we cannot have a proper predicted value. Similarly, in speech recognitions, we need to pass proper syntax, proper statement. So this is the difference between non-sequential data and sequential data. I hope it's clear. Now, let us talk about why RNN. All right. So this is a great question that we can ask oneself, that why recursive neural network? Why not ANN or something else? See, there is a difference between every architecture is made for its own specific use, right? So let me give you and make you understand with an example. Like hi, this is one entity. My name is Sam. This is a data set, small data set. But this one, I hate this. This is a small data set, okay, in which if the sentence is neutral or positive, it gives one, it gives zero, and if the statement is negative, it gives. All right. So first of all, let us understand that why ANN would be a not best fit, and we can use RNN. All right. So if we count, see, first of all, this is the first challenge that comes to mind is we need to vectorize the words first. These are the challenges that we face. So let us go with the challenges one by one. We need to vectorize words first. So this is hi, my name is John. Could we could not directly feed to the numerator. We need to convert it into a vector. So how do we convert it into a vector? We could use one hot encoding. All right. So one hot OH, one hot encoding. Now, what does it does is it's pick up the most of the values, such as this is like 1, 2, 3, 4, 5. So this is like five values. I love this movie. This is 1, 2, 3, 4. It's four. Then I is a common, so that we won't consider this. Hate is a unique word one. This is also common movie. This have two. Oh, sorry, this have only one. As this above I, this and movie are common, so we'll take this one. All right. So this is five unique things. This is only four unique things. All right, this is four. The total is 9, 10 unique things. So how do we represent this now? So if I want to represent my statement one x1 into a vector format, I would state it as if I want to give, see, these are named as 1, 1, 1, 2, 1, 4, 1, 5. All right. So if I give you this, see, we name it like this, and we are working with this height first. So we pass one values at a time in RNN. So this would be like this. This is like 1, 0, 0, 0. This is now if I want to print my how my could be converted into vector. This would be 0, 1. So this is similarly just we can go on, and then we could have a one proper matrix for a review statement that is. So see how we are actually converting this, and then we pass these vectors into a neural network. 3, 4, 5. For the first statement only, I'm talking about. We have to pass so many vectors. All right, so many vectors, imagine. All right, and then if I see how many weights it would develop, so see, this is like five five vectors. So if I calculate, so this is 10, 10, 10, so 10 each. 10 feature each, because in total we have 10 features, so 10 by 30, 40, 50. So this, the input size is 50 now. Now if I multiply it with this 50 into the 150 weights would be required into 3 neurons that are getting hidden there. So equals to 150 weights. 150 weights will be required. So see how computation increases, right? So, and I see, first of all we have faced the challenge one, that we need to vectorize this. Second, zero padding. Now what is the zero padding? Unnecessary computation is when zero padding means, when we see, now I have put it here, 5 vectors, so I'm getting a weight of 150 that I would require to compute this. Now if I put this sequence, now this would be like 4. So how much it would be? So it's like 10, 10 this would be 40. The second sequence would be 40 into 3, 120. You see how input is varying. For this I have only one, 10, only one vector would be required. So 10 into 3, 30. 10 into 3, 30. It would require only 30 new. So see how data is varying, input data is varying. Have you ever seen in any ANN or any architecture where we, define that, it automatically adjusts the input? No, right? So this is the problem. So now one thing you would be asking that, okay, I want to do one thing, that I will take the most maximum size, that is one. But what if someone gives you a bigger sentence than this? Suppose 100 has come instead of 10. You have like, instead of 50, like 5, you get 100. Then this input size increased. Then that is your bigger value. So this is into the network that is called as zero prime. You try to increase the number of values to maximum, but what if something else has come? Then the problem creates over there. The text input is the vary size. So this is same that I have discussed about, how the inputs varies in between, right? Prediction not accurate in ANN. See, because no sequence is there, we are not following any sequence, and we are not following any patterns, and we are just uh, giving it randomly, and we are together. I mean, whole value means a whole vector together, right? You don't have to do like this. If you're passing a whole vector together, then what's the use of, and how will you predict? It is a difficult task for ANN. So hence, like disregarding the sequence. So these are the challenges that we face in the RNN. So that's why we don't prefer ANN, and rather we have developed a new network that is an RNN. All right. Now talking about the inputs in the RNN, as I said, yeah, as I said you here. See, as I said you here, we have 3 sentences, and let us see what are the unique words in this. This is like, for the first we have 3 unique words. Three. Here we have one unique word. One. Here we have not, not, and good is also repeated. So we have here in total how many words we have repeated, right? So 3, 4, 5. So in total we have 5 features. So total in we have 5 features. And just like before, if I want to, these are the unique words, as I said, and this is how we represent. This is like in the previous slide, as I said, we represent this. And if I want to put it into a whole matrix, then it would be like this. All right, so this is the movie vector. This was the boss vector. This is the good. This is the bad. This is not. All right, so this is how we actually create or give the input in the current neural networks. All right, now I was talking about, see, this is the architecture of neural network. All right, this is a normal feed-forward network in ANN that we directly feed forward directly in layers and get the answer. But in recurrent neural network, there is no speciality, that when you compute your input, that is xi, wi, you also compute. See, you get an output for this, right? But in the recurrent neural network, your new input will also be there, plus your output of that hidden neuron with the weight will also be there. So this is how you will compute the weights. means one vector we have given, it has went to the calculations, it has given some output, and that output is again taken as input for the hidden layer. And just not this we, but it also takes an input for this also, this also, this also, this also. So it itself also with the other hidden neurons, it goes with the input. So this is how we compute. All right, so just remember one thing, that in the hidden layers we are again, see, we have passed one vector here, one vector is passed, then we compute something, we get an output, then we pass another vector, but with that vector we are also passing the output of that thing, and hence we are like this, and then we get an image, and then we add them and we get the value. All right, so in the first, what, like, you will ask me a question, what about if I'm just passing the vector at the first place? So then you don't have anything, right? So at that time we take random values. These are some random values allotted to the weights, and random values you take as a output. All right, this is for the first instance, and then you keep on multiplying the sequence, sorry, the output sequence I was talking about, the random value. And then you keep on putting the sequence that you properly get an output. So this is that for first sequence you get a random value, but then for the other sequences it totally depends upon what output you have got. So this is the architecture of the recurring network. It is yeah, so this is the architecture that I was talking about, right? So in this architecture, just a second. So see, as I said you before, we take input into the terms of time steps and input features. Now, what is this time steps? See, let us see again. Again, let us understand. This is the common word. This is the first. You have three common words, unique words. Then we have only one. And here we have one. 12, 5. Again 5, right? We are doing the same example. This is a sentiment. Okay, so it's good. This is bad. Now, when we pass it through a RNN, okay, it's something like this. All right. So when, as I said, like when we create a vector previously, as I said, you when we create vector something like these plus these, some vectors we have created. So we pass these vectors, these numbers, from 0 some these numbers into the neural network, and then when we pass it to, and when we pass the vector to this, so at that time we pass it as time step and input features. Now let us see what is time steps. Time steps is like when this one particular thing is inputted, this vector, I mean, small vector. So this is counted as one time, one, like t is equal to 1 we have given. All right, what are the features? Number 5. So this is 1 comma 5. All right, so these are like 1 comma 5, and then for example when we pass the walls, so into the architecture, this has a loop here. This is a start. So when we pass the second word, this would be time instance is equal to 2. So now this is 2 comma input features 5. What are the input features? Input features means the same, this is 5. Now t is equal to 3. This is the code. T is equal to 3. When you pass 3 is equal to 3, we get something like this, 3 comma 5. All right. So I hope you guys have understood like how exactly we transfer this thing into a RNN, and how an RNN works exactly, right? So the basic, the let me summarize this for you to a different. All right. So how would we see? This is a little complex architecture, I know, to understand, because you are also computing these weights, and then you are getting some output of it, and then you're also computing again for OY and WI. So this is the double calculations that you're doing for each neuron. So when the data input size is large, you can imagine how computations will be. So just giving you a little summary how the model would be. So this is the hidden layer, HA. To simplifying, this is the input vector, and this is the output that you get. And in between, we have the hidden layer. This goes as self loop, this loop. Oops, this is a loop. Right. And as I said, these are the timestamps and time steps, and this is the input feature that we input, and this is how we actually give an input to the RNA. So I hope this is clear with you guys are clear with the architecture of the RNA. Now let us talk about the applications. Applications. Now talking about the applications, we can see we have wide range of applications in various fields, including NLP, that is natural language processing, right? Natural language processing, especially I've seen in today's world, that is ChatGPT and speech recognition, text generation. This is the architecture that is running behind it, right? Time series analysis. Then we have image and video processing. We can use this if we have a series type of values for this, then we could definitely use this. Robotics, and it can be used to control and learn from sequential sensor data. So see, everything is sequential here. It works on sequential. And we have at last music and audio processing, music generation, because that notes are into a sequential manner, audio synthesis and speech synthesis. So these are some applications of RNN. I hope you guys are clear with the recurrent neural network and also the convolution neural network. We also had a look with the code of the convolution neural network and learned how to implement it. And all right, guys, so this is it for the session today. And tomorrow we have the different session, that is computer vision. And I invite you all to please attend that event and let your friends know about that event, because it's a event based on computer vision, which is a great topic to learn about. As in this far that we know and we have knowledge of CNNs, neural networks, machine learning. So please do join that session and invite your friend also. Thank you. Have a good night.